Right, I think we are live. Okay, so hello everyone, welcome once again to our online quantum chaos seminars. Let me check. I think we're good. Okay, sorry about that for the people watching live. I was just here myself. That was the problem. Okay, so once again, welcome. Thank you for tuning in. Today, as you know, we're very happy to welcome our speaker, Charlie Nation from University College London, who is going to be giving our online seminar. Charlie did his PhD with Diego Porras at the University of Sussex, where he worked on studying quantum statistical physics in systems far from equilibrium. We'll hear some about it today. He actually got his PhD just a few weeks ago. So congrats to him. You should say congrats in the live chat. And he's now, as you can see, he's now starting a new position to be a postdoctoral fellow at University College London. So thanks again, Charlie, for agreeing to giving this talk. We're very excited about it. And take it away whenever you're ready.
Brilliant, yeah. Thanks, Pablo, and also thank you, Peter. I'd like to thank you both for organising this. It's a privilege to be able to talk about my work to everyone. So yeah, I'll be discussing thermalization in closed quantum systems. So the key motivations behind this will be looking at some key questions. So like the first one will be on how statistical physics can be seen to emerge in from unitary quantum dynamics, so within a closed quantum system. Then we can take this question a step further and ask also how classical Brownian motion can be seen to emerge in such a system. And a key theme running through will be, can we use the theory from the developed for the first two questions and apply it to quantum devices in a way that's useful in order to characterize them. So we'll see what I mean by that in later slides. So I'll take a kind of detour halfway through to look at some applications. So the general scenario that we'll be looking at is some kind of lattice or some chain. I'll be talking in context of spin chains, but generally just some lattice model that will initialize in a pure state. So then, because it's a closed quantum system, it will evolve under unitary dynamics to some other state. And if we, at late times, measure some local observable, this local observable was found to be in a state described by an effective thermal ensemble. So this is a surprising result in some sense, because the state remains globally pure, yet it's described by an effective ensemble state. So the puzzle as to why these systems evolved some ubiquitous thermal state is really the key problem at the heart of statistical physics that I'll be aiming to describe today. So qualitatively, what we're looking for in such a system is essentially, I'll describe things in terms of a system observable, which is our local observable, and this will decay in time, starting from some non-equilibrium state. And the state that it equilibrates to when we describe thermalization will depend only on the initial state energy. So crucially, this shouldn't depend on the particular microstate that you initialize the system in. It just depends on the energy of the initial state. Secondly, fluctuations around this equilibrium state should decrease exponentially with system size, where n here is our, say, the number of qubits in our spin in the chain, or so the size of the system. So the question really is, under what conditions can this ubiquitous behavior be seen to occur? So we'll note that generically this is observed in non-integrable quantum systems. So in integrable models, thermalization in this sense doesn't necessarily occur, like the ensemble can be different and things like this. So we'll be specifically talking about non-integrable systems today. So one attempt at explaining this and at guaranteeing these thermalization in the sense of the previous slide occurs is called the Eigenstate thermalization hypothesis. And this hypothesis can be written as an ansatz on the matrix elements of observables. Right, so your observable matrix elements in the basis of eigenstates of the many-body Hamiltonian is written in two parts. So with the first part here, the diagonal part of the eigenstate expectation values, right? So the diagonal parts here are just the expectation value of an observable in a given eigenstate. These are conjectured to be equal to some thermal expectation value that depends crucially on the energy of the eigenstate, right? So this is equal to the microcanonical average in some sense. So this, and this guarantees that your system will thermalize in the sense of the condition 1 on the previous slide, that it will be given by some microcanonical average. The second part, here we have the inverse of the density of states, which essentially means that this term is very, very small. And the second term guarantees that the fluctuations are small, because the fluctuations depend on the off-diagonal matrix elements. And we have some smooth function again. There's a function of energy and the difference in energies between the eigenstates. And this function should decay when the difference in energies is very large. And there's some stochastic variable here. So essentially, this ansatz guarantees thermalization, and it's been numerically very well studied. And it gives us also some nice intuition, right? That it's eigenstates themselves that thermalize, and we see the first part of this intuition from the diagonal term, which is that the eigenstates themselves give thermal expectation value, right? So this gives us the first part of this intuition, but generally the ETH is a very strong assumption to be making off the bat, right? Like it's without some better justification, it guarantees thermalization, but it's not so physical in terms of it's just assuming it. So we'd like to be able to base it on some more general assumptions that are a bit more physical. Secondly, it leaves an open question of which observables does it apply to, and finally, like it doesn't describe the dynamics to equilibrium. It doesn't tell us how a system gets from a non-equilibrium state to an equilibrium state, and that's something else that we'll discuss moving forwards. But the first thing is that we want to base the system, our approach, on some more physical assumptions. So I'll describe these assumptions first. And the first and most important assumption that I'll be making is that of chaotic wave functions. So this is where quantum chaos enters the picture in terms of this theory. And the idea is that, so for some Hamiltonian written in terms of a non-interacting part and then a coupling part, where the coupling renders the whole system non-integrable, if we write the eigenstate of the full Hamiltonian in terms of these non-interacting eigenstates, we have some distribution of these coefficients C that we can suitably coarse-grained described by a probabilistic theory that's approximately Gaussian. This is what would be meant by chaotic wave functions. But we'll see that an important addition that we have to make to this Gaussian theory is that each of these eigenstates are mutually orthogonal. And we'll see that this effective interaction due to the mutual orthogonality of the eigenstates is actually very important to keep. And we can't actually just keep the Gaussian part. So we need to include these effective interactions. And the important thing that will be used throughout is this function lambda. And this function governs the kind of envelope of the chaotic wave function. So a smoothed version or a coarse-grained version of the wave function distribution itself is given by this function lambda. So in practice, this is just a spin chain, or the calculation of this on a spin chain, where through these I'm just turning on some interaction that renders the spin chain non-integrable. And we see that actually this Gaussianity of the probability distribution, again, this has just been coarse-grained to obtain some probability distribution. the Gaussianity of this does occur at the same sort of scaling as when a more standard marker of chaos in a quantum system, like Wigner-Dyson energy level statistics, occurs at kind of the same time. So this just shows that we have some, this is also a good marker of quantum chaos, or some marker of quantum chaos that occurs at a similar time to markers that are quite normal. Moving forwards, like a model that we can obtain or describe analytically in terms of this chaotic wave function ansatz is a random matrix model. And the model that I'll be using was introduced initially by Deutsch in the early 90s on the seminal work on kind of beginning the ETH. This model was given by some non-interacting part, H0, which is simply a linear distribution of energy levels with some constant separation. And then each of these energy levels is coupled together by the random matrix coupling. So you can see we have the same sort of structure to this random matrix theory that we had to the systems we'll be trying to apply it to. And for this model, using the Gaussian wave functions, again, we can actually calculate analytically what this function lambda is. And it's given by a Lorentzian of some width gamma that's proportional to the coupling strength. And this is obtained by this average over the possible random matrices, which should be this average over V. But more generally, when talking about the chaotic wave functions and not just the random matrix theory, this average over random matrices could be thought of as just some kind of coarse graining procedure, like how I obtained the probability distribution for the spin chain. So it's not necessarily, the theory in general doesn't necessarily have to be a random matrix theory. But we already, as well here, see an intuition similar to the ETH, which is that the eigenstate itself forms this effective microcanonical ensemble in the sense that an individual eigenstate is present over some energy width from some energy, from its central energy. So we have this eigenstate thermalization starting to be present in terms of individual eigenstates here. So an important property that we'll be using as well is called self-averaging. So this will be very important in making the theory of thermalization, and that's essentially the property that a single realization or a single instance of the observable dynamics from this random matrix theory is indistinguishable from the ensemble average. So the observable dynamics is indistinguishable from the average over random matrices. So this can actually be analytically shown by looking at the variance of this, and this can be shown to be equal to 0. And actually this is shown as a consequence of chaotic wave functions and doesn't require the specific random matrix model. So it's using the ansatz of chaotic wave functions. So this, and also I'll stress that this is valid for a given non-integrable initial state, non-equilibrium initial state, and a given observable. So there's no averaging over initial states here. There's no averaging over observables. The key averaging that we do is over these random matrices, or more generically over the kind of coarse-grained chaotic wave function. And this is shown to be self-averaging analytically. So the additional assumptions that we'll make just quickly before describing the method will be that we're looking at local observables to some part of the general system. And the key feature here is essentially that the observable only makes transitions on the system energy levels, and this leads to some sparsity condition, so that it can only have certain transitions being made. But also, I'll just quickly note that this is also valid for the specific form of the assumption that we make. It's also valid for observables that are present on the entire support of the Hamiltonian, but as a sum of local observables. So we can have something like the global magnetization here as included. So it's not necessarily like some small local part. And the second condition is what we call smoothness, which is essentially a more of a mathematical condition, but it's required for the calculations. But intuitively, what this can be described as is a kind of ability to take a coarse-grained version of the observable here outside of the summation, and essentially the requirement here is that over the width lambda, over the width of this function lambda, which is the width of a single eigenstate, the average of the observable doesn't change too quickly. And it doesn't take too much to convince yourself that this is actually the same as the ability to define a microcanonical average that varies smoothly in energy, right? So without this condition, you wouldn't be able to define an average over observable matrix elements that depends smoothly on energy. So back to our initial discussion where we have to have some microcanonical average that doesn't depend minutely on the initial state. This is essentially a requirement that without this you wouldn't obtain some smooth microcanonical average.
Can I ask a quick clarifying question?
Yeah.
How does that differ from the diagonal assumption on ETH, where your diagonal elements basically behave as a microcanonical average?
So this isn't an ansatz on the matrix elements in the non-interacting basis. Right, so the actual assumption that this is made on is essentially saying in the basis of alpha of the non-interacting eigenstates, in the basis of H0, we can create some average, some coarse-grained version of this.
Okay, thanks.
Right, so it's an assumption on in a different basis essentially, and using some other function to smooth it with. So it's a much weaker assumption than that. So yeah, now we've got all our the assumptions in place. We can sketch the method that will be used to calculate some the say dynamics of observables, or the things we'll calculate later. So we'll calculate for some function f. The approach will be to rewrite this in the non-interacting basis of O alpha beta, and then apply this self-averaging condition, which doesn't apply to these observable matrix elements because they're written in the non-interacting basis, right? So V doesn't, they don't change with V. And then from this we can integrate over this correlation function by taking the continuum limit, assuming that this density of states is approximately constant over the width of a single eigenstate. So the last thing missing is this correlation function, and this can be obtained from the Gaussian or from the chaotic wave function distribution. And what we see here is one term that we obtain as if there were no orthogonality condition. So ignoring this orthogonality condition, we have something that looks a lot like Wick's theorem, where we just have the 4-point correlation function equal to the product of 2-point correlation functions. So this is quite a simple term. That the important point is that there's an additional term that is precisely due to this orthogonality condition, and this gives a non-trivial 4-point correlation function that has to be considered. Right? And this is simply due to this orthogonality condition. So now, using this approach, we can start to make calculations with this theory. So the first one is that we can calculate the ETH. So the diagonal part can be written like this, where we see that we have here this smooth function of energy as the diagonal matrix elements of the observable, and it's given by some microcanonical average. And this was, it should be stressed actually, this was already obtained by Deutsch in the early 90s. But where our approach allows us to extend this is to the off-diagonal matrix elements as well. And we can calculate the functional form for these. So this is specifically for the random matrix theory model that can be applied to some quantum systems, but this can be generalized for different lambda. And also this is for quite a simple observable that's diagonal in this basis, but it can be generalized to different observables as well. So the key point here is that we've got some functional form that fulfills the full ETH from some more general conditions. So these are the specific assumptions again. I think perhaps more importantly is that we can compare this to an exact diagonalization of a spin chain system, and we see that this random matrix model does compare quite favorably here. So I'm not going to describe in detail this Hamiltonian because the important point is that it's non-integrable, right? And it just gives some effective description in terms of the chaotic wave functions and in fact the random matrix theory. And we see here that we get a good description of the eigenstate envelope, of the observable, and of a different observable that's got a bit more of a complicated structure. This can be obtained analytically as well. Sorry, one second. So now we'll move on to discussing dynamics. So I should say from describing the ETH, what we already have is that thermalization is guaranteed, as I discussed before, right? So we have, from these assumptions, we've seen that the system is guaranteed to decay to a thermal equilibrium and have small fluctuations. But to take this a step further than the ETH, we'd like to be able to discuss both the dynamics of observables and maybe get some more information on the form of the fluctuations. So those are the next two things that I'll discuss. So again, for the dynamics of the observables, we can just rewrite this in terms of our correlation function and perform the integral over that. And the result here is this following equation. So this has got three kind of key parts, which is the decay to equilibrium. And we have some modulation by this term, which is the free evolution under the non-interacting Hamiltonian. And then we have the long time average value, which is shown to equal the microcanonical average. And importantly here, we actually have that this long time average value would be totally wrong if we didn't include this orthogonality condition. So to get a consistent description of the decay to equilibrium, the mutual orthogonality of individual eigenstates has to be considered. So here again, we have a comparison of this equation to the spin chain model. And once again, I'm going to say that the particular form of the bath and the interaction isn't particularly important. It's just that it's non-integrable. And this non-integrability generates the universal dynamics that's described by the effective random matrix theory. But we do get to keep, given from the last equation, we do get to keep the system Hamiltonian, which is describing this free evolution under H0. So this is what gives this precession when we have some more complicated observable in the system basis, right? So this describes is for various different observables in slightly different conditions with also different initial states. So here we have a more typical quench procedure where the initial state is an eigenstate of the non-interacting Hamiltonian, but also here we have, it works very well for more general initial states like product states, for example. And this can be shown analytically as well. So it's not, we don't assume this analytically and just apply it here. We have some more generic initial state. So next we can start to discuss the fluctuations and see if we can get some functional form of the fluctuations away from equilibrium, additionally to just knowing that they're small, right? So first I'll clarify between two different forms of fluctuations that we can observe. The first being the time fluctuations, which are what we expect to exponentially decrease in system size for long times. And it's these that are relevant for thermalization that I've discussed earlier. But secondly, we could also discuss quantum fluctuations, which are just the variance of an observable at a given time. And it's these we'll see are more relevant for the discussion of Brownian motion, which we'll get onto later. But these can already be found simply from the previous equation for long times, as was given by this microcanonical variance. So using the broader recipe that we've outlined earlier, the time fluctuations can be calculated from this diagonal ensemble picture of the fluctuations. And it should be noted here that actually in this equation, it requires an 8-point correlation function, because these off-diagonal matrix elements here are in the interacting basis. So before performing self-averaging, you have to transform this into the non-interacting basis, and this gives 8 different coefficients C. But this can be performed quite easily with this theory. So the larger correlation functions are totally doable. And we obtain this functional form for the time fluctuations. So immediately you can see that this is proportional to the inverse of the density of states, so it's very, very small. But I think more interestingly, we have this factor of the decay rate here of gamma. So this describes a kind of fluctuation dissipation theorem, where we have the time fluctuations of the system proportional to the inverse decay rate. So this is some equilibrium quantity as being proportional to a critically non-equilibrium property of the system, of the decay rate. We also see here a comparison to an exact diagonalization of the same spin chain here for different system sizes. So we see that this functional form compares well. So the different dots here are different initial states. So immediately from this, I'll now discuss a couple of applications. The first one being quite a simple fluctuation relation, which is comparing essentially the ratio of the two types of fluctuations that we saw before. And we see here actually that there's this microcanonical variance here, described by this, which is actually the same as the quantum fluctuations. So the ratio of these two things is proportional to this. And what we can see here is that actually this fluctuation relation provides a relation that gives the density of states in terms of 3 measurable quantities. So we have the decay rate, the time fluctuations, and the quantum fluctuations. Each of these 3 things is obtainable from, say, an experimental process that would measure the decay to equilibrium of an expectation value of an observable. And we can see again that this a numerical experiment here comparing the density of states at the initial state energy obtained from a numerical experiment from this fluctuation theorem is actually compares very well to the exact diagonalization. So a second possible application of this approach, which is a little bit more involved, is more in a specific like an initial framework, will be where we can characterize some quantum device by initializing it in some infinite temperature state. So this device could be, say, a spin chain model or something like this. So we have the device initialized in some infinite temperature initial state, so a fully decoherent state, and then act on it with some probe qubit. So this is specifically a qubit with some trivial non-interacting dynamics. So in this case, we can recalculate the fluctuations, or the fluctuation dissipation theorem. What we actually see here is that this proportionality constant is proportional to a term that's an effective Hilbert space dimension of the device Hamiltonian. So there's also this factor of the average density of states, which I won't go into in detail, but the important thing is that this is quite simple to calculate for a given model. So what this allows us to do is obtain the scaling of this effective Hilbert space dimension with system size. as well as actually obtaining this number directly in some cases. So what we can see here is, for example, if we have a fully connected device of, say, n qubits, what you could say is that the Hilbert space dimension of this device is 2 to the n. But this is not a particularly useful characterization if there is local interactions or disorder, or you could say trivially, if the device has some section that's totally decoupled, the total Hilbert space dimension you could describe as 2 to the n, but in reality, the dynamics doesn't explore that size of a Hilbert space dimension. So the aim here is to characterize some effective Hilbert space dimension in terms of a fully coupled device. Right, and that's what's obtained here from the spin chain again. So we obtained from a fit here that for a fully connected device, we would obtain this value for the slope, but actually for a locally coupled spin chain device, we numerically obtain some slightly smaller value, but still an exponentially increasing effective Hilbert space dimension. So this is kind of what we would expect, but the key claim here is that this number, this effective dimension, is a useful characterization of the kind of effective complexity of some quantum device. And also this scaling I'll just mention can also be found from changing only the coupling strength, and so it doesn't need to be obtained from a fit to different system size values. So that might be relevant for potential experimental applications. So moving away now from more specific applications and finally discussing the emergence of more classical Brownian motion. So we've seen that something resembling quantum thermalization can be seen to occur from the assumptions that I've outlined. What we'd like to do is take this a step further and see if classical Brownian motion, a kind of prototypical example of classical statistical physics, can also be found. So here I'll be comparing this to what's called the Ornstein-Uhlenbeck process, which is simply the Brownian motion of a classical particle trapped in a harmonic potential driven by some thermal noise. Right. So some key results for this the Ornstein-Uhlenbeck process are that the decay to equilibrium is exponential, and here I've set just the equilibrium state as 0. We have an equipartition theorem here for the fluctuations of the kind of observable, which is the position. And finally, the time fluctuations that we've already seen are 0. So comparing to what we've already got, actually, we can see that 2 of these things are already fulfilled. Right? We have the exponential decay to equilibrium from the random matrix theory, and we have the third thing, which is, in the classical limit of a very large device, this tends to 0 exponentially even. So what we want to do is try and obtain the equipartition theorem, and this is wants to be done for a closed quantum system, right? So, and initialized in a pure state. So to do this, we make a kind of analogous quantum system, which is one where the system, or our observable, lives on a system that has a harmonic energy spectrum, and that energy spectrum is made up of many energy levels. So these are the 2 additional assumptions that we'll make, talking specifically about how to obtain an effective Ornstein-Uhlenbeck process. And then we can rewrite the density of states here in terms of some effective kind of inverse microcanonical temperature beta. So this is where the temperature comes from in our pure state, essentially. So we don't have an ensemble, we have the temperature arising from the density of states. So using, again, essentially the same recipe for calculations, we have that the quantum fluctuations describe an equipartition theorem. So we have that this this function beta describes an effective inverse microcanonical temperature. But more interestingly, I think, is that we have this equipartition theorem emerging on the level of individual eigenstates, right? So we have this eigenstate, so this this microcanonical variance, right, which is an average over a single eigenstate, also has this equipartition theorem for it, which we call the eigenstate equipartition theorem. And this extends the intuition that was afforded to us by the ETH, where the ETH says that thermalization occurs at the level of individual eigenstates, and here we see that even like stronger result will be that something like resembling classical Brownian motion can occur at this level as well, where we see an equipartition theorem at a given effective temperature for individual eigenstates of a closed quantum system. So just to compare the results then from the random matrix theory and the classical Brownian motion, we have an exponential decay to some equilibrium value, very small time fluctuations. So the quantum fluctuations are given by some equipartition theorem, and finally the comparison should be made between the average that I should have said earlier. This average is over trajectories of the kind of the Markov process that is the Ornstein-Uhlenbeck process, and this should be compared to possible measurement outcomes, like the average over measurement outcomes that we have here. So this motivates a description in terms of quantum trajectories of many measurements, right? So what can we describe a process of quantum measurements making use of this kind of intuition that we've obtained here? So in looking at this, the last thing we'll look at will be quantum jump trajectories in these systems. So this is where we have many successive measurements on the thermalizing system. So this is essentially unitary dynamics except for the projective measurements. So then in between these measurements, we have thermalization dynamics described by the random matrix theory, and more generally the chaotic wave functions. So what we essentially have is a measurement quench at intervals, the same interval as the measurement interval. So the picture here is that we have some initial state, we wait some time and we make some measurement, and this projects the observable state onto some value, and then there's another thermalization process, and so on. This occurs repeatedly. So what we can do is say that between measurements, we can define some conditional probability. And this conditional probability can be written in terms of some local observable, some local operator, essentially. So this is described by the same, is given by the same assumptions that we've made before, and can be described by the random matrix theory model that we had. So that describes our evolution in between measurements. So now we want to look at the effect of a given measurement, which is that we can obtain by averaging over, say, looking at, say, this point would be averaging over possible hypothetical measurements in this central point. And what we obtain is that this is actually equal to the equation that we had before. So we obtain some measurement independence of the average dynamics, right? This is given by the same decay, regardless of whether there was a measurement made or not. And this gives an effective description of the system in terms of a Markov chain. So on average, an average over possible quantum trajectories, the dynamics is the same as if measurements were never made. It's the same as the expectation value dynamics. So this was previously conjectured and has been numerically studied before, but here we have it occurring analytically for a closed quantum system. So again, in practice, comparing this to an exact diagonalization, and this is of a kind of a harmonic spectrum, a quantum harmonic oscillators, but it can be done as well for a spin chain as before. We have some Zener regime, which due to finite size effects, the measurements actually freeze the dynamics because there's been essentially no dynamics in between measurements. But this is simply a finite size effect, and outside of this regime, we see that the decay rate of the average trajectory actually tends to the same decay rate as the expectation value. So we see some kind of confirmation that actually this trajectory is given by the same as if there was no measurements made at all, on average, that is. So a given trajectory is still obviously only really definable with given measurements. But what this allows us to do is what we've obtained from describing this in terms of some conditional probability, is that we can borrow some ideas, say, from stochastic thermodynamics and define some local entropy growth in a system. And defining this local Gibbs entropy, we can actually show analytically that this local Gibbs entropy increases in time. So we can make this link using these hypothetical measurements to stochastic thermodynamics from closed quantum systems, and see that this entropy is non-decreasing. So finally, I'd like to just summarize, which is, and from what we've seen, is that the random matrix theory picture, and more generally this picture in terms of chaotic wave functions, provides a foundation for the ETH based on assumptions that are kind of less stringent than the ETH itself. And furthermore, we can use these assumptions to take it a step further and describe things like the decay to equilibrium. We can describe the functional form of fluctuations, and it's quite useful in comparison to realistic quantum spin chains. We can further observe the emergence of classical Brownian motion from the closed quantum systems. So this by deriving things like the equipartition theorem, and see that the ETH can be, the intuition of the ETH can be extended in a sense that these occur on the level of individual eigenstates as well. And we've also looked at a couple of possible applications of this, and see, for one, that there's possible to inference of an effective Hilbert space dimension in terms of measurable quantities. So finally, I'd like to thank everyone for listening, and thank again Pablo and Peter, the organizers of this, and also thank Diego Porras, who's my PhD supervisor with whom I did all of this work. So yeah, thank you. If there are any questions.
Okay, great. Thanks a lot, Charlie, for that excellent talk. I thought it was really interesting. And first of all, there's a lot of congratulations in the chat for you.
Great.
And also a few questions. So first by Ivan Deutsch, can you clarify the operational definition of the effective Hilbert space dimension? What does this dimension quantify?
Yes, okay, so the best way I would kind of quantify this is in terms of the effective number of eigenstates of the system that are non-trivially involved in the dynamics of the observable, right? So that's kind of the picture I would give it. So it's not the full Hilbert space dimension, it's just a kind of effective number, an effective dimension of the Hilbert space dimension, is what I would say.
Okay, I think that probably partly answers the follow-up question. Is this related to other measures, for example, based on the effective number of spins that are entangled with one another?
Effective number of spins. So it's quite different to the effective number of spins itself, because it's, but I think it's probably quite related to some other measures. But I think the key point that I'd like to stress about this measure is that it's potentially experimentally obtainable, because we can write it down in terms of experimentally measurable quantities, and that also it's just it's a useful measure of an effective Hilbert space dimension of the system.
Okay, then we have some more questions by Manuel Munoz Arias. First of all, how can you guarantee the dynamics is being driven by the thermalization rather than the measurements?
Yes, so that's a good question. One thing that we kind of implicitly assume in the measurements is that the measurement itself doesn't drastically change the energy of the system. So this is quite intuitive because like a local measurement on a large globe, a larger system shouldn't change the energy too much. But yeah, we kind of require this. But also the measurement itself, on average, can be seen to have no effect if the bath part is causing a thermalization dynamic. So if the measurement was causing this thermalization dynamics, you wouldn't really get this decay to a thermal equilibrium that you would see in these types of things. But,
okay. Next question is, can I think about this emergent Brownian motion as a diffusion process in Hilbert space?
In a sense, you get potentially. I think so. I'd like to maybe discuss this more to understand the question a bit better. But like a diffusion process in Hilbert space. Yeah, I'm not sure. Maybe potentially. I'd like to. Yeah.
Yeah. And then there's one question which you might have already answered. Is the effective dimension connected to the portion of Hilbert space accessible during the equilibration process?
Yes. Yeah, definitely. That's a nice way of picturing it, I think. Like, yeah, the effective. I'll say again, just the effective number of eigenstates of the full Hamiltonian that's involved in the equilibration process or in the dynamics of the system. So that's the key measure that it's giving.
Okay, great. Then I actually also have one question just for myself. So in the first part of your talk, the derivation really depended on the proximity, basically, of an integrable / non-interacting Hamiltonian. So for Hamiltonians that are slightly perturbed integrable ones, you also expect pre-thermalization. Could you also describe this using this framework?
Well, potentially in the sense that so actually H naught in this system doesn't necessarily need to be integrable, right? Because you can split it into a system part and a bath part. That's the important point is that H naught has the system and bath as not interacting with one another, but the bath part can be a non-integrable system. As far as describing close to integrable systems and kind of pre-thermalization of the model, what would happen in that sense, I think, is something like this part of the decay equation that depends on the evolution under H naught would be the part that captures this pre-thermalization process. So instead of this precession that we had in the spin chain, like that was quite a simple case, you'd have a pre-thermalization kind of captured in that part, in the integrable part, and then a slower decay to equilibrium captured by the effective random matrix theory. So I think potentially, yeah, like pre-thermalization would be very interesting to look at from this model, and I think potentially could be, yeah.
Okay, great. Thanks a lot. And also, once again, thanks from the chat for this great talk. So I think that concludes this week's seminar. And next week, we'll be back with Juan Diego Urbina from the University of Regensburg. And he'll be talking about universal signatures of many-body chaos and integrability through semi-classical theory of quantum interference in Fock space. So just as a reminder, if you want to get updates about these talks, you can either subscribe to this channel or subscribe to the mailing list, and there's a link in the description of this video on how to do so.